also perhaps want to just take a moment to acknowledge and thank all the speakers from yesterday, particularly those from Work Package 5, who I think the research they presented was really great in helping to stimulate discussions throughout the day. Also to acknowledge the keynote speakers, especially I think Mike Rasenberg and even Klaus, for the insight that I gained on the CLP process, and I think I learned a lot, and I feel like we spend a lot of time from a scientific perspective focusing on the science and perhaps lose touch with what is actually happening in that policy space. And as scientists, we perhaps get frustrated because we don't always understand why the science we're working on isn't being implemented in the policy space, but perhaps we don't fully understand it. So maybe I need to spend a week in the shoes in Helsinki of Kostas and Mike to better understand exactly what they face on a day-to-day basis to appreciate their perspective. So I really wanted to take a moment to acknowledge that as being really important. Now, focusing on the science aspect within this project, I've been tasked to develop a multimedia fate model to evaluate the fate and transport and exposure of chemicals that may potentially be identified as persistent and mobile. And in this context, I'm effectively building on the concepts of fugacity. And there's some inspiration behind this in how science can have an impact in the policy space, because this publication from Don Mackay in 1979 really represented a paradigm shift in the way that we address or understand, characterize, quantify the environmental fate, transport, and exposure of organic contaminants in the environment. He proposed the use of fugacity, which is a principle that's been around since 1901, and recognized its utility in understanding the fate of and transport of organic contaminants in the environment. It's very useful because it describes the escaping tendency of a chemical to move from one environmental phase, for instance, to another, so from air to water. And what's nice about it is because it has units of pressure, Pascal, you can quantify the concentrations of chemical in the environment. But it also provides a conceptual tool, because you can sort of visualize chemicals need to move from areas of high pressure to low pressure in order to achieve an equilibrium. And so appreciating that chemicals are always working towards an equifugacity in the environment is helpful for understanding a little bit how they move depending on their physical chemical properties. So it represents a convenient method for defining thermodynamic equilibrium. And indeed, this publication and the work of Don Mackay really was critical in helping to formulate how we evaluate exposure of chemicals today. So talking with colleagues from RIVM, I've also appreciated the work that are here today that they have done in terms of early days of working on SimpleBox and SimpleTreat, which are now really the engine behind EUSIS. And so the way that we evaluate exposure in chemicals is really based on these fundamental principles which we still use today. So I think it's helpful to understand how that has really been useful in informing our policy understanding and how we evaluate the risk and exposure associated with chemicals. Now, the challenge that I have when thinking about chemicals that may potentially be persistent and mobile, and we saw these criteria yesterday. I'm not going to talk about what they are. They're very specific criteria, but one of the issues that arises, and we heard a little bit yesterday, is that a lot of them are not all are neutral organics. Most of them are actually ionizable organics, such as acids and bases. And here I just plotted out, for instance, 150 of the high priority category chemicals that are identified in a Uber report that was lead author was Hans Peter on, and in this space I've just tried to show, which I don't know how well that comes out in terms of the color scheme, but you can see that a number of them are organic acids and bases. The x-axis in this case is the octanol water partition coefficient, and I just sort of drew lines in there to show that chemicals to the left of that space are typical of mobile chemicals. And the reason I'm using KOW is to emphasize the fact that KOW is what we use to get at KOC for most of these chemicals. And so there's a relationship that we connect between KOW and KOC that is also important to reflect upon in terms of understanding where we derive these values from. So we need a model then that is capable of dealing with ionizable organics. However, since ionizable organics, or the ionized species, doesn't have a pressure associated with it, the concept of fugacity proves to be somewhat problematic when trying to model these chemicals. But it's important to understand, nevertheless, the ionization, the species that is ionized in the environment, because it has an impact on how the chemicals sorb to different environmental matrices. So this is just a plot to effectively illustrate the difference between acids and bases. And for I cannot come to grips with this technology. Whoa. I'm not going to touch that anymore. Yeah. So we have acids and bases, and as you can see in this plot, the idea is that the bases, when they become more cationic in scope, that their partitioning tends to be stronger than the neutral fraction of the chemical, and that's because the positive charge of the base tends to interact with the predominantly negatively charged species that are associated with the soils that we're looking at. So you tend to have higher sorption for cation organic bases that are in the charged form than for acids. The acid, because you have a negative charge, tends to have a repulsive interaction with the soil, and so you tend to see lower sorption potential for the acid than you do for the neutral form of the chemical. So understanding then the fraction of ionized species in the environment relative to the neutral species becomes important to some extent because it can give you a better estimate of the fate and transport and therefore the exposure of the chemical in the system that you might be looking at. However, so thankfully there is a model that actually tried to address this issue. This is conducted by work from Antonio Franco as part of his PhD work and this publication in 2010, where they describe an activity-based concept for the transport and partitioning of ionizing chemicals. And one of the things about this approach is that it does borrow from fugacity, and instead as opposed to fugacity, it's using activity as a way to explain how chemicals interact between different environments. And through the work of Antonio Franco, he also came up with these different algorithms which are continued to be used to try to evaluate the partitioning or the KOC values for organic acids and bases, for instance, relative to the neutral fraction. And this can be input into the model, or is input into the model that I've developed, so I'm effectively using this model, but also want to draw attention to the fact that the model has flexibility so that if you actually have the KD value for the chemical you're looking at, you can input that directly and override these algorithms, which have some level of uncertainty associated with them. Now, the model that I'm developing is novel in that it is a multimedia, multi-soil layered model. So the ionized, the MAMI model from Franco is being used in this case, but I've just added effectively 20 different soil layers to the model to provide flexibility for dealing with different soil systems you might have. The key component with this model is sort of defining then an unsaturated soils, surface soil, a deeper unsaturated soil, and ensuring that you have a saturated soil compartment, which is representative of a groundwater system. This saturated soil is connected to the sediment bed to allow for some flow between effectively the surface water and the groundwater, so that you could have some recharge to the groundwater systems that at play. And this is being done based on Darcy's law, so we're using principles from Darcy's law to help explain the movement of chemical between the saturated soil system and the sediment bed. And so we have these different systems that are at play within this model structure that I'm trying to use in this case. One of the key challenges in this component then is how to parameterize the soil compartment. So I should stress that the model that I'm using is representative of a generic unit world model environment, and again, that's what's used in the uses. So we have very generic properties that we define for the soil system, for instance, that we're working with in terms of a fraction of organic carbon. But because we're dealing with ionizable organic chemicals, it's important to appreciate that different soil systems may cause chemicals to move through the system in different ways in terms of the leaching as they interact with different types of soil horizons that they may find in different environmental systems. Now, thankfully, the groups that have worked on the focus models have actually done a lot of work in characterizing different soil systems across Europe. And they have identified a number of systems that are meant to be representative of worst and best case scenarios in terms of soil systems and leaching of chemicals through those systems, and these are well characterized. And I can then use these soil systems to parameterize the model that I'm working with. We have these phase 1 chemicals, which you've also heard about. So the PFAS, which are effectively dominated by strong acids. In other words, the pKa values for these chemicals are typically less than 2. We have triazines in our set, 5 of which are neutral organics. We have 6 organic bases and 2 organic acids, and this is then likely to have ionized fractions in the environment based on the range of pKa values associated with these chemicals. And we have triazoles, which are typically dominated by, or split between the neutral form of these chemicals and organic acids, as their pKa values tend to be greater than 7. So the results, I'm going to just give you some preliminary results from the model exercises based on the level 3 model calculation, which effectively describes a system that's at non-equilibrium but is steady state with respect to emissions into the environment. The parameterization of the soil system in this case is based on the focus model as described for the Hamburg scenario. And I've chosen this particular soil system because it represents the worst case leaching soil. And you can kind of get a sense of that because this is a sandy soil system with a relatively low organic carbon content associated with it, and in this instance the groundwater depth is 2 meters below the surface, and so it lends well to this multi-soil layer model that I have, because I can then introduce a number of different layers that are representative of these different soil horizons in the model system that we have here. So if I take this and input the various phase 1 chemicals into the model, I can get results in terms of the concentration, for instance, in the groundwater. Of course, as a modeler, we always have to bear in mind that there's a scenario where we have garbage in, garbage out, and we have to be careful that we have very good data that go into the model, or feed into the model in terms of the input data. Now, the PhysChem property data, I feel fairly confident that they're okay. I've done what I can in terms of the soil parameterization. But I do want to flag that we don't have any emission data for any of these chemicals. I am, as a preliminary estimate, just using the tonnage bands that I have available to us for these chemicals, and if I use those tonnage bands as an input, I'm assuming that 100% is emitted to soil as a worst case scenario to understand what might end up in the groundwater system that I'm looking at. I can then compare these data to environmental monitoring data that I've summarized from the Norman network in terms of the database they have for each of these different chemicals, and obtain a relative indication of the performance of the model that I have here. So these are just some preliminary results then to illustrate the performance of the model. The red boxes are illustrating the model estimate, and the box and whisker plots are providing you an indication of the distribution of the concentrations for each of these chemicals that is reported in the Norman network for groundwater specifically. The numbers above each box represent the number of samples that are contained within the distribution that's there. Now, I think as a quick glance, you can see that for a number of these chemicals that, given the crude approach that I've taken in terms of emission estimates, that actually I'm within the range of concentrations in groundwater that have been reported in the monitoring data, which is somewhat comforting, but also bearing in mind that it could just be serendipitous. So more work should be done to sort of ensure validation around the performance of the model. On the other side, there are a few chemicals, 4 chemicals where the concentrations observed are significantly higher than the monitoring data. And to this, I just attributed to the fact that because I don't know what the actual emission data is, it's most likely driven by uncertainty due to the emissions. But the model, however, does provide an indication that perhaps the estimates would be conservative in scope, but somewhat realistic, so not more than 2 orders of magnitude greater than what we're seeing in terms of the monitoring data. Nevertheless, there are, of course, a number of challenges and limitations that are necessary to sort of explore as I kind of move forward in utilizing the model. Clearly, emissions data represent a fundamental input parameter that need to be better understood. Also, I think I want to reflect on the importance of the environment-specific variability. How important is it really? And one of the things I'm beginning to realize that perhaps the model soil system is not necessarily that critical to understanding, because it may only introduce an uncertainty of a factor of an order of magnitude, whereas the emissions data could represent uncertainties of several orders of magnitude. And so in this case, it may not be necessary to worry so much about the parameterization of the soil system, but really focus on getting better emissions data. I also, in this model then, haven't evaluated the effect of drinking water treatment on the removal of these chemicals in the system that we're looking at. So the model then, of course, is conservative in its approach, but it may be of interest to better understand how drinking water removal would help to mitigate exposure to these chemicals from a human health perspective. The monitoring data, I think, are really important, and we're going to hear more about these reflected in the presentations from both Abhishek and Sylvia later on. In this case, they are going to also include the surface and groundwater data that are contained within the Norman database. But as we kind of go forward in looking at those data and how they fit into the risk matrix, I just want to put up this one chemical to show you the distributions for tebuconazole, for instance. And this is somewhat typical for a lot of the chemicals. The statistics are shown here. Those are box and whisker plots, and you only see the whisker. And the whisker is being driven by one data point, which is high for this concentration, for this chemical relative to everything else. The median concentration, for instance, is 0 here, which effectively means it's below the limit of detection. So the majority of the data, therefore, are below their limit of detection. The mean value, however, is slightly higher, and the maximum value is 65. So in the data we're using always the maximum value in the risk matrix we have, but I just want to draw attention to the fact that these are based on these kinds of distributions. And when we think about the uncertainty, I think it's important to reflect on what that distribution in terms of monitoring data look like, because it also influences potentially how we interpret the data from an exposure perspective. So with that, I thank you for your attention. I'm very happy to...
ZeroPM. Zero pollution of persistent and mobile substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.